Hi everyone, I'm Patrick, and I'm presenting a view for any occasion, implementing the C++ standard library proposal for any view. My alternate title. So a little bit about me. I'm a licensed professional electrical engineer since 2022. Currently, I'm implementing RISC-V device kernels for an AI hardware company, Torrent. And previously, I worked for a high-frequency trading firm between 2020 and 2024. And before that, I began writing firmware for embedded systems, particularly STM32, but a couple of other architectures as well. I enjoy metaprogramming and fractal art. I have a link there with an interactive fractal rendering program. And this is my first full-length conference talk. So try to go a little easy, but I'm definitely open to questions and feedback. So let's get started. So the topics I'm going to cover in this talk is first the motivation for the standard library proposal, some performance benchmarks, and then going over the design choices, and then some of the challenges in the implementation. So motivation, enabling range-based library APIs. So the ranges library is great, and it's like expression templates are really nice and composable. But we'll get into that in a second. The other motivation factors, standardizing established practices. There's a few third-party libraries that implement something similar to this type erasing mechanism. We're going to talk about the pros and cons of those libraries' implementations and their design choices. And then, like generally, we want a generalized type erasure for ranges with an acceptable cost. And so part of that is defining what we would want to consider that to be acceptable. So back to the ranges library, expression templates. They're great for declarative programming, not ideal for API boundaries. APIs are about separating interface and implementation. Expression templates, at least in the way that ranges library defines them, they unify it. And so the type information exposes all of the implementation details, which means that you're not really getting a benefit from separate translation units. So we want to figure out how to improve that. So there's two cases on an API boundary. You can make it a function return type, or you can make it a function parameter. For function return types, the idea is that you have a library created range that the user consumes. And you want to make the library implementation freely modifiable without affecting the user's ability to consume that. You don't want to break your users. And then with function parameters, you have a user-provided range that you want the library to consume. And there's a few ways to handle that now. Usually, it's a tailor-made range type provided by the library that the user is now obligated to construct with the data that they want to pass into the library, and that's not great either. It has benefits, but it's just we want something more standardized. So existing practices, there's std vector, which is not a type erasing mechanism, but is often used as that because of its convenience. And then also in C++20, we now have span. And it's very performant. It's great for very specific cases, borrowed contiguous sized ranges. But it's not a general solution, and that's what we're aiming for here. So existing practices, there's the ranges v3 library, and also boost ranges provide their own implementations of any view. In the ranges v3, it allows you to customize the reference type and what they call the traversal category, or in C++20 terms, the iterator concept. It does not allow you to customize the R-value reference type, which is the type when you are moving from the view. And it also does not allow you to customize the difference type. Boost ranges, their any range does customize the traversal category as well, and the difference type and the reference type. It also does not customize the R value reference type. And it only supports borrowed ranges because the implementation type erases a pair of iterators. So it's definitely pre-C++20, where the iterator and Sentinel are assumed to be the same type. So it also doesn't support uncommon ranges. So let's try to define what we consider an acceptable cost for generalization. So in the general case, we want to type erase any viewable range. Now, that's not to say that we have one class that can type erase anything. We want something like std function, where it's a class template and allows the user to configure the specific properties that they want to preserve in the type erased mechanism, such as the input category, the reference type, etc. And so in a general solution for a type erase view, we want a default of a wide constraint. So by default, we want to be able to type erase as many things as possible and have a very narrow interface. So in this case, like input range would be the widest constraint with the narrowest interface. And so we want to follow that for all of the configurable properties that are available. And then the acceptable cost, when comparing in an apples to apples against standard vector, we want to make sure that when iterating over it just once, that it can be faster than the equivalent existing practice with approximating vector as a type erasing container. So getting into the performance, let's define our design space with the existing practice, assuming it to be vector, and with the proposal of the ranges any view. So before we get into the actual benchmark, I want to reiterate, no pun intended, what how the for loop, the range-based for syntax works. It gets the range and stores it as a auto-ref, and then it gets the begin and end iterators. And then from those, it iterates the begin, advancing it until it's equal to the end, and then dereferences the begin on each iteration. So we have a comparison, we have the increment, and the dereference. And these are the three points that need to be type erased. So keep that in mind with the benchmark. So in our design space, let's say that we're creating an API for a database. And in this API, we have a function getProducts, and it takes a parameter of, for a given product, the min available quantity. And so the database is going to internally store a vector of these products, and the query is going to return some range that represents a filtered view. So we'll have three cases here. In one case, we'll want to return a vector of string view, the string views being the names of the products. We'll call that the eager approach. The lazy approach is the any view of const string. And now, like span, that is an element type, so that's not saying that it will copy any strings. It actually will be dealing with const string L value references. And then lastly, we have what I'm calling the fused approach. There is an optimization in any view that begins with the forward the forward iteration concept, but is not possible in the input iterator concept, at least not in the generalized case. In the fused the fused implementation, it will have that optimization, and I'll get to that later in the talk. So to set up the database, we'll generate some random products using uniform distributions so that we're not taking advantage of any patterns in the data or anything like that to improve branch prediction or anything. And then, so this is the benchmark for the eager case. We just initialize a database with the global products that are initialized to the max size, and then take the first in elements of that global thing, store it in the database. After we've done that, then we measure the performance of calling the get products function and then subsequently iterating over the return value once. So this is the implementation of the eager approach. We just declare a vector and then loop over the products in the database, do our filter on the min quantity, and then push each name back into the results. Remember that it's storing string view, so it's not copying any strings here. It's just constructing a stream view from each string and then returning the results. In the lazy approach, we can use the ranges library and construct a range adapter pipeline that allows us to declare how we want to apply these views over the products in the database. So we can apply the filter view and then subsequently apply the transform view. And then once we have that lazy range or lazy view, we can type erase that with any view. So in that case, the get products really doesn't do any work. The only work being done is whatever it takes to type erase that. So in the case of eager versus lazy, unfortunately, it's not great performance. It's not drastically bad, but it's definitely something we want to see improved. And keep in mind that the performance here is including the time that vector takes to allocate and not just the time it takes to iterate over it. So that's it puts the any view in a pretty bad light. But once we enable that optimization that's capable of being added, at least for the forward iterator concept, we start seeing some benefits and the ability to type erase. So the implementation currently uses virtual polymorphism because in C++20, the easiest way to get type erasure that's available in a constant expression is to do virtual const expr. I'm currently exploring some optimizations that will allow me to inline the vtable, so that may reduce cache misses, and then implementing the vtable as storage aware, which would allow me to eliminate any branches in the virtual dispatch, and then also reduce the size of the class layout by not having to keep track of whether the type erased target is stored in the class layout or allocated. Because if the vtable is aware of that, then I don't need to branch in order to do that. It's just going to be a static dispatch. So what was this? Yeah, so this is our existing benchmark, and I want to propose another benchmark. So let's say that we get the products, and then all we want to do is loop over the first 100 of those. So, I mean, can anyone want to take a guess what the outcome is going to look like for this between the eager and the lazy approach?
I think your lazy one's going to be
much
better.
Yeah. So, you know, the lazy approach doesn't scale with the size of the database. It's only a function of the number of elements that you loop over. And so with the eager approach, there's no way around paying for the time it takes to allocate the vector and initialize all of the elements, even if you don't consume all of them. And now I understand that with a database implementation, you could provide a more fine-tuned function that also performs the take for you. But this was a violation of the open-close principle. You want something that doesn't require modification to meet new use cases. And so with lazy type erased views, it allows you to have a more generalized API that's able to meet more use cases just off the bat. So let's get into the design. First, I want to talk about what's the difference between a view and a range. I want to talk about iterator concepts, range concepts, reference type, what does it mean for move iteration, and then also why do we want to customize the difference type. So a view versus a range. Any view, a instantiation of any view is a view. It type erases a range. So a range is just anything, colloquially it's just anything that has begin and end that returns an iterator and a sentinel. And a view is a range, but has the additional properties that it must be constant time movable, at least as a function of the number of elements that it's a view of. And then it's either should be non-copyable or a constant time copyable if it's capable of doing so. And so either of those allows it to satisfy the requirements of a view. So customizing the iterator concept. By the way, this is the synopsis for the declaration of the AnyView class, as well as the options that allow us to customize the properties. So that's what you're looking at here. So I want to go over the different iterator concepts and what each of them look like when you're instantiating the AnyView. Like, how do you instantiate the AnyView to type erase each of these concepts? So the input is the first option there, and it's the default iterator concept that's on AnyView. So if you don't specify it, that's what it's going to be. Almost any range is viewable, with the notable exception of initializer lists and a handful of other cases. But for the most part, most of them are viewable. The iterator behavior of an input range is that you can't assume it's copyable, so it may be move only. You can't assume it's default constructible either. And we just constrain the post increment to return void because the requirements on that are loose enough that we can't make any assumptions about what that thing returns. So an example of something that can be type erased as an input range is the iStream view. And so this only satisfies input range, but it does not satisfy forward range. So moving on with the forward concept, this allows us to add the optimization that I referred to earlier, where we can fuse the virtual dispatch for the increment, compare, and dereference functions, so that we're only paying for the cost of a single virtual dispatch per iteration. In the case of forward range, input range is no longer viewable. So if you have an AnyView of forward, that means that you can no longer type erase any input ranges. So like I was saying earlier, it widens the interface that's available to you. You're allowed to make more assumptions, but it also constrains the things that you're able to type erase. So the iterator behavior for a forward range is that now you can assume that it's copyable, you can assume it's default constructible, and that it's weakly comparable with itself. So you can test equality or an inequality. And the post increment returns the iterator by value. More generally, it satisfies the multipass semantic requirement. And so it has equality preservation on the post increment. So some examples of, oh yeah.
What does weakly comparable mean in this case?
Weakly comparable just means that, actually, that's a good question. To my understanding, it supports equality and inequality, but it does not support any of the like less than or greater than or anything like that. So some examples of forward ranges are forward list and the lazy split view, and so they're forward ranges, but they're not bidirectional ranges. So bidirectional range, the iterator is now decrementable, so you can go backwards. An interesting thing to note about the AnyView is that calling rbegin is still ill-formed. And the reason why is because just because you can go backwards on an iterator does not mean that the range is necessarily going to allow you to start from the end, because it additionally requires either the sentinel is dereferenceable, which most of the cases in the ranges library it's not, or that it's a common range. So that would make the iterator and the sentinel the same type, therefore the sentinel being dereferenceable. You could provide it if the any range was additionally random access sized, but a workaround for this is to just wrap the any view in a common view, and then you get the rbegin for free if it's able to provide it for free. Otherwise, you get runtime overhead where it stores the iterator and sentinel in a variant internally, and then you get a runtime dispatch every time if you want a common view on top of the any view. But by default, any view is just going to be non-common, so the sentinel and iterator are always going to be different types. So some examples of bidirectional ranges include list and filter view, because now you can go backwards, but it's not something that provides random access support. All right, so random access ranges. An interesting thing to note, and something that I didn't understand when I first got into this, is random access does not imply sized. You can have a random access range where the size is not known in constant time. So for the iterator behavior, you now have the comparable with inequalities other than not equal. You get subtractability, so you take the difference of two iterators and now you get the difference type as a result. They're advanceable, so that you can advance any number of elements and not just one at a time. And same thing for decrementing, you can go backwards any number of elements. And they're indexable, so when you index, it's similar to the dereference, except it's basically an addition with the difference type followed by a dereference. Yeah.
Do you know of an example of a view that is random access but not sized?
A null terminated C string.
Okay, cool.
Additionally, it's contiguous.
And iota view without an upper bound.
Yeah, that's another good example. So for random access ranges, some additional examples like I have here, iota view and dec. So dec, it is not stored in contiguous memory, but you can still random access into it. And then iota doesn't store anything. It's just a view that provides a random access interface, and dereference just computes a value for you. So, and then finally we have the iterator concept for contiguous, which, as I mentioned, contiguous also does not imply size. And in the semantic requirements for a contiguous iterator, it behaves exactly like an address. In fact, in the libc++ implementation, it will convert your custom contiguous iterator into an address and use that instead. So if you don't meet the semantic requirements of an address, it's going to bite you. So some examples of contiguous ranges include vector, span, and as of C++26, optional, with the range interface that provides a range of exactly 0 or 1 elements. So in addition to the iterator concepts, we can provide properties of other range concepts such as size, borrowed. I touched on common. I'll get back to that. A const range, so calling begin and end on a const qualified range, and then copyable. So for size range, you just pass the sized option to the second template parameter, and you have to opt into this explicitly because it's not implied by random access or contiguous. Once you enable the sized option, it allows the size function on the any view to be well formed, and it also allows the iterator to be subtractable from the sentinel type. So without the size property, that subtraction is disallowed. Yes.
So contiguous or random access ranges do not imply size, but doesn't size imply those?
No.
Is there an example where?
I don't have one on it. I did have one a few weeks ago and I forgot, but yeah, we've taken it offline.
Is the list an example?
Exactly.
The list is sized, but
Oh, true. Yes. Yeah. Good point. So list is bidirectional and sized, but it is not random access or contiguous. Thank you.
Or if you take any input range and you pipe it into take, then you have the size count.
Yes.
The double-ended queue has random access, but it is not contiguous.
Mm-hmm.
The queue?
Yeah.
Standard.
Yeah. Cool. Okay. So moving on to the borrowed option. In some cases for views, the iterators may outlive the range. And in this case, we want to make sure that the semantic requirement is met that we don't use that when that's the that we can use them when they do outlive the range, and that we avoid using them when their lifetime should not outlive the range. So a function can take the range by value and return iterators obtained from it. So in the case, like if you have a borrowed view, you can pass it by value to a function, and that function is allowed to return an iterator from that because the iterator doesn't need the range to remain within its lifetime in order for you to validly dereference the iterator. So some examples are maybe counterintuitively to some that L values of any range are considered a borrowed range because an L value's lifetime does not dictate the validity of dereferencing an iterator that comes from it. So you can pass an L value of a vector to a function, and it's perfectly valid for that function to return an iterator into that vector because that vector's lifetime is not tied to the scope of the function. And then a string view is another example. So,
and it's like you're just sort of assuming the lifetime is somebody else's problem. Like,
yes.
yeah. It's just it's borrowed anyways. I'm gonna let you get it, but it's borrowed.
Mm-hmm.
It's not my problem.
Right.
Yeah.
Yeah, and so ranges provide some protection where if you don't opt into specifying that the view is borrowed, you'll end up with a dangling sentinel type as the return type of some of the ranges algorithms, the constrained algorithms, if they check that you're trying to access it from a non-borrowed range. So you'll get the compilation error if you try to use that as an iterator. So any view does not support common. As I said before, it's mostly unnecessary. The cases where that's really useful is kind of the legacy algorithms, and it's a really easy workaround to just wrap it in the common view because the common view will provide that interface without any runtime cost if it's capable of doing so. And if it's not capable of doing so for free, then you can get the wrapped iterator sentinel in a variant so that you have a little bit of runtime overhead and you're still compatible with the legacy algorithms that require a common range. But because of that and the additional complexity it would lend to the implementation, it just wasn't deemed as a high priority to support. Similarly, constant access to views is something that is currently in the effort of being deprecated. I had mixed feelings about this when I first saw it, but the motivating factor is the ability to significantly simplify the required implementation for each new view that's added to the range library. It's a lot less work to get a functioning implementation, and arguably the const qualification on the begin and end methods is kind of a leaky interface because it could be in some sense considered an implementation detail that you're able to treat it as a view when it's const qualified. Yes.
Yeah, just a quick disclaimer. This paper hasn't even been discussed yet. So
Mhm.
it's not any official position on that. It's just my opinion.
Fair. Okay. Thanks. Okay. So it also supports copyability. By default, we want move only. This was something that was discussed in SG9. Initially, the proposal was to make move only the opt-in and copyable the default. But I made the argument that this is kind of counterintuitive to what the rest of the options provide, because by default, the rest of the options had a wide constraint and a narrow interface. But if you enable copyability by default, you actually get the opposite of that. It's a narrow constraint and a wide interface. And when I started testing the implementation, I realized that I had to keep special casing copyable when I was testing the constraints, because you kind of have to flip that in order to test it independently of all of the other available options. And it just makes more sense in my mind as a kind of a symmetrical way to enable options on the type erasure. Note that copyable does coincide a lot with borrowed, but it's not necessarily that always the case. I don't think these examples were necessarily counterexamples of when they don't coincide, but it was just examples of things that are considered copyable by the view semantics are L values and then subrange, because it just holds two iterators. Or iterator sentinel, I forget. Yeah, it's an iterator sentinel, so they don't necessarily have to be the same type. All right, so moving on from the options, now we want to customize the reference type. So there are a couple of cases where the reference type might not be an L value. Most of the case, it makes sense to make that the default. But for example, vector of bool does not return an L value reference to a bool when you dereference its iterator. It returns a proxy object. And so in that case, when you type erase it, you might just want to make the reference type the value type, like a PR value bool. And that would be compatible with type erasing a vector of bool. Another example is transform. When you have a projection, it's pretty typical of the projection to return a PR value. And so you might need to override the reference type in order to be able to type erase a transform view. Move iteration. So an interesting example of this is zip view. So zip view combines multiple views into a single view, where when you iterate over it, what you get is a tuple of the references from each of the individual views. So you're iterating over them in lockstep. So the reference type is actually a PR value tuple, where the element types are going to be the reference types of each of the respective views. So when you think about moving from a zip view, it doesn't make sense to what am I trying to say? Like the tuple is not the thing you're moving from. It's each of the individual elements you're moving from. So the R value reference in that case would be a PR value tuple of R value references for the element types that correspond to each of the ranges that you're zipping. And then enumerate's another special case where it just returns a pair. And then lastly, the difference type. So an iterator might not have the same domain as an address, and we want to account for that. So when you're type erasing something, maybe putter diff is overkill, and you want a narrow one. Or in the extreme case of iota view, if you have an iota view of size t, the difference type is implementation defined. It's okay with C++20 semantics, because in that case, the difference type is allowed to be an integer-like type, but pre-C++20, it must be strictly an integer. An 128-bit implementation defined integer is not considered integer by pre-C++20 standards. And so you might run into the case where it's not compatible with legacy algorithms, but we still want to be able to type erase that, because we're in C++ almost 26 now. So So let's get into the implementation. I wanted to talk about some of the interesting challenges that I faced while implementing this, particularly the small buffer optimization. Part of the challenge was, interestingly, type erasing the constructors of the views and the iterators, because you have to copy the iterators, but with virtual polymorphism, you can't declare a virtual copy constructor. That's not a thing. And then I ran into an implementation detail where I wanted to be able to constrain virtual functions and found that the language didn't allow me to do that. And I'll go into the workaround that I had for that. And then lastly, the fused iteration optimization that I enabled for forward range iterator concept and above. So the small buffer optimization, we want to make sure that it still satisfies the strong exception safety guarantee. So when you move from a view, it must be no except, or specifically any view, I should say. I don't know that holds in the general case. But for any view, we wanted to make it follow the strong exception safety guarantee. So that move constructor must be no except. The in-place storage requires that the type erase type has a non-throwing move constructor, and that you're using any view at runtime, because currently, as of C++26, we still do not have a way to perform in-place type erasure in a constant expression. And then lastly, we want to ensure that the in-place storage is sufficiently small and well aligned to fit the type that we want to erase. And so if all of those are satisfied, then that's great. But if they're not, then we need to allocate it. So here's what that looks like in the implementation. So an implementation of the detail of the any view that I've implemented contains what I'm calling an intrusive small pointer. And the reason it's intrusive is because the interface that it type erases must implement methods to facilitate the type erased copy and move construction. So because we don't have a virtual copy constructor or virtual move constructor, we have to facilitate that in some way. And so they're just named methods, move to, and copy, that allow us to type erase those operations. So because that's something that the interface has to opt into, I called it intrusive. So the intrusive small pointer has some in-place storage, and it also a union with a pointer. And so when we type erase this, we must choose whether to store it in place or to allocate it and point to it. And then lastly, we have an index, which is just an enum of a Boolean that allows us to keep track of whether it was stored in place or allocated, that we will need to check when we dispatch. Let's see. So the way that we use intrusive small pointer, we use it both directly in the AnyView implementation and its exposition-only iterator, because both of them have to be type erased. So for the AnyView, we have a sufficient in-place storage to store a vector of t, as well as the vtable pointer that's required to be stored in place. So that'll be 3 pointers plus an extra pointer for the vtable. And then for the iterator, we have 3 pointers for in-place storage, so that it's sufficient to store a vtable pointer and 2 pointers, because in this implementation, the exposition-only iterator actually stores both the iterator and the sentinel of the view that it type erases. And so I figured for a naive case, let's say that it's actually addresses that we're dealing with. We want to be able to store those in place and not have to allocate. This is an implementation detail, and it could be changed. This just was an arbitrary choice that I made at the time. So the next challenge was type erasing construction. I mentioned it in the interface for the intrusive small pointer. As you can see, when you declare a virtual constructor, that's not allowed. and the problem with that is that naive usage of this would require slicing the object. If you think about virtual classes, you can't use them with value semantics. You have to have a reference or a pointer to a virtual class. If you were to hypothetically allow the language to implement virtual copy construction, that would mean that you would need sufficient storage to store the derived type. But because it's not compatible with value semantics, you'll end up slicing the object. So the only way that you could actually use this is if you use the placement new syntax, and that's not something that is widely used. So I figure that's why they disallow that. And like I said, the derived classes have unknown size. So unless you're in a context in which that's known, you don't even know how much storage to provide in order to copy that. So that's why it's facilitated through those other methods that are provided on the interface. So we have interface movable, which is the base concept, and then interface copyable, which subsumes that with the additional requirements that it adds a copy to for in-place copy construction and a copy for the allocated copy construction. And if those are satisfied, then that allows us to provide a type erased interface for a copyable view. So here's the implementation of what those look like. So on the top left, we have the copy constructor of the intrusive small pointer, which is constrained only to copyable interface. We initialize the index, which is telling us whether it's stored in place or allocated. And then we check that, and if it's in place, we perform the in-place copy. Otherwise, we get the copy of the allocated pointer and store that. And then the move construction, which must be no except in order to satisfy the strong exception safety. We still store the index. When we check it, we perform an in-place move construction of the target type in the case that it's stored in place. Otherwise, we take the pointer of the allocated target and exchange it with a null pointer so that the move from object is no longer storing anything. And we store that in the pointer of the intrusive small pointer that we're move constructing. And so this is the only way that you can implement strong exception safety guarantee with small buffer optimization. So you need to be aware that in the move from state, if the target type was allocated, it's no longer holding onto an object. But it's okay because you're actually allowed to delete null pointer, and you can do that without a branch. That's perfectly valid. So we don't have to pay for the cost of a branch in the destructor to check if an object is present, because either it was stored in place, in which case we still have an object that's in a move from state and we call its destructor, or if it was allocated, we can unconditionally call delete on the pointer that's present there, because either it holds a valid object within its lifetime or it holds a null pointer, both of which are valid to call delete on. So back to the problem of constraining virtual functions. Actually, I don't think I touched on that yet, but I did talk to somebody about that earlier today. So the language allows you to constrain normal methods, and the way that this works is it makes it conditionally visible within a particular specialization of the class template. So if the constraint is not met, it's as if that method doesn't exist in that specialization. But unfortunately, the language does not allow us to do this for virtual functions. And the reason I wanted to do this is because it would significantly reduce the number of class templates I had to define in order to satisfy all of the combinations of properties that can be type erased. Yes?
You wouldn't happen to know why can you not constrain virtual functions? Why?
I don't know. I think it would be an interesting feature to have in the language. The only thing I can think of is that it may be potentially confusing to somebody that's writing a virtual class, and then, you know.
I guess it's the derived classes could.
The derived
alter
class would
or
also
remove it.
have to conditionally define it with a constraint. So, was there another question?
I was just going to say that it changes the vtable
Yes, and that was my intention, as I did
Yeah.
want to change the vtable, and that would be great. But we can't do that. So instead, I have to unconditionally define it and constrain the body to only be implemented if the concept is actually satisfied. Otherwise, I call unreachable. And this is an implementation detail. It's not user-facing. This doesn't allow users to call the unreachable code because the publicly exposed method is properly constrained. This is a virtual method on the intrusive small pointer, which is not directly exposed to the user. So the unreachable case is truly unreachable. It just allows us to express an arbitrary return type without having to produce that in the case where our implementation doesn't satisfy the concept necessary to implement it. And because it stood unreachable as C++23, the Beman AnyView implements a polyfill to provide that in C++20 with compiler intrinsics. And then lastly, the fused iteration is a single virtual dispatch that has so in general, let's back up. The virtual dispatch has significant overhead, and that was the majority of the cost, at least in our benchmark, where we weren't performing any work in the loop other than forcing the benchmark not to elide the access of the value. But when we're just measuring the cost of the iteration, the virtual dispatch has a significant overhead. So it's very valuable to reduce the number of virtual dispatches if that's possible. So in multipass guarantee, we can implement a virtual next method that returns an iterator cache object. And so if the reference is an L value, the iterator cache is simply a pointer. And so when we call next, it increments the iterator, compares it to the sentinel, and if it's not equal, then we store the iter cache from the reference of the iterator. Otherwise, you know what? This screenshot is outdated. This was when I unconditionally implemented it as an optional of the reference type. So I apologize for that. But so there's two cases where we can implement this. If it's a forward iterator concept and above, and the reference type is an L value, or if the reference type is a trivially copyable PR value. And so in that case, it's safe to store it in the optional engaged or not engaged, and then when we return the trivially copyable type from the cache, I think that's on the next slide. Here we go. So you can see on the operator star, when we return from the cache, we simply dereference that, and we don't have to check because operator star has the precondition that it must be valid. So we don't have to pay for the cost of checking the optional because that is performed in the equality comparison with the sentinel. So yeah, back to what I was saying. When you have a PR value that's trivially copyable, we just return that from the cache copied, and because it's trivially copyable, that has almost no overhead. And then for L value references, we just dereference the address that we store. So it's conditionally a null pointer, but we check if it's a null pointer in order to ensure that the range-based for loop does not access that. So this cache object does increase the class layout size of the exposition-only iterator, and it prevents RVO, the dereference, but the performance benefit, as you saw earlier, I think was provably better than without fused iteration. So it's worth the cost. And unfortunately, that's all I had for today. So I was expecting a lot more discussion because when I did the practice, there was a lot of discussion that ended up running into an hour and a half. But I apologize for that. Are there any questions now? Yes.
So, virtual functions conditionally removing. Could you conditionally delete them?
Say the question.
Going back to the other sort of
Yes.
rabbit hole that I started there. Apologies. But the sort of you have virtual functions that cannot be constrained. Could you have deleted them?
No.
No, because you can't conditionally delete something, can you?
Yeah, I don't think you can
but-
delete virtual functions.
Right.
Oh,
You have to have an implementation.
Class.
You have to have an
Right,
implementation
yeah.
in the vtable in order to construct the object. Yes.
Yeah, I mean, I think in order to conditionally have a virtual function, you just conditionally derive from a base that provides the virtual function. Right? If you didn't want to derive from multiple base classes, you could have a hierarchy where you have like a common base, and then you use templates to add the successive bases. It would require quite a bit of boilerplate. And then you have to structure the implementation that actually drives from it, especially so that it has like a linear inheritance hierarchy too. But it could be accomplished. I mean, but the example on the slide works, and because your users don't call the virtual functions, they're never going to call the unreachable ones. It just blowed in the vtable. But
Yeah, and I am currently exploring an implementation that uses the C++ 26 static cast from void pointer in a constant expression, so I could just completely do away with any virtual functions at all. And that allows me to have more customization over whether I want to inline the vtable or continue pointing to it, and a couple of other optimizations that come with that flexibility. So, yes.
What sort of things in your implementation, if any, could be improved or modified in some way with P2996 reflection?
Jonathan actually opened up an issue on the Beman AnyView project with a couple of suggestions I've yet to implement. One of them was improving the case for random access iteration. I could significantly reduce the size of the vtable by providing a function that dereferences the iterator given a particular difference type, and I could use that to kind of bootstrap the entire iterator interface from much fewer vtable functions. And then for contiguous, specifically contiguous sized, I believe the iterator and Sentinel can just both be addresses at that point, in which case I don't have any virtual dispatch at all, other than constructing the iterator at the beginning of the for loop.
Do you have a guess on how that would improve the performance?
In the contiguous range, I'm going to guess significantly. In the random access, I would not venture a guess. I don't know.
That's fine.
Yes.
could you go back to the options for the interview?
Yes.
Error type.
Yeah.
This one. So the last three, it seems like you always have to OR them with one of the first.
Yes.
5. So you can't just pass a size or anything like that.
Yeah. If you pass a size, you're going to hit a static assert in the class template definition that tells you that it must be at least input category. And the reason for that is, or at least I'm not speaking on behalf of SG9, but this is just my personal opinion. If we require that the input category is passed explicitly, that will allow us room in the future to expand support to output iteration category potentially. So if we require that to be explicit, we might be able to expand the scope for more options in the future.
Right.
So if it were implicit, then that would be breaking existing code if we were to propose that.
That's good thinking.
Yes.
So for type erasure in general, one of the things that has started to bother me is the fact that we pick one storage policy, and so we end up with function and function ref and maybe shared function and unique function and who knows what.
Yes.
And I just wonder when we're going to move away from that and actually come up with a way to solve this fleet of storage options in the initial paper.
I too would love to see this. I don't believe that is currently AnyView's job, but maybe a potential future, even more generalized type erasure mechanism maybe something that requires language support would be interesting to explore. Yes.
I assume you know more about type erasure than I do. Do you know do you know if anything like Louis Dion's Dino library has been proposed for standardization?
I do not know the answer to that. I'm familiar with his Dino library, and I like it a lot. It's trait based, right?
Yeah.
Yeah.
But I think it's quite I think it's a C++ 14 library, so it could probably be.
Yeah, it's definitely not const expr.
But it is a preprocessing library.
Right.
It relies on token basting to do most of its operations. It's not even type safe.
Oh. I don't see any more questions. I had one bonus slide. I was anticipating a little more pushback on the benchmarks, but you guys were really easy to convince today. So I had one more case where I tested the pre-allocated vector against any view as well. And thankfully I found that it wasn't significantly different from the vector where we naively perform the resize or the reserve during the iteration where we're adding results to the vector as we accumulate. So I just wanted to share this as another data point. As I tried very hard not to contrive these benchmarks and to make them reasonably well compared, where we're testing the work that's being done as fairly as possible. But yeah, it is just another data point I thought I'd like to share. Yes.
So given this, would you feel comfortable using this in a performance-sensitive context?
Yes.
Okay.
Yeah.
I didn't notice any template parameters for allocator. Is that coming? Yeah, I'm sorry.
No, that is not coming.
Okay. All right.
I mean, the allocator is going to be a template parameter of the target type that you're erasing, not of the interview itself.
So are you going to use that allocator when you're allocating your internal state?
No.
So that's why you would need it.
I understand. I think there's a lot more advantage in performance potential if you allow the freedom of the implementer to be able to choose the implementation details of the storage type rather than making that part of the public interface.
Yeah. On the other hand, there's correctness.
Fair.
Without if you don't pick up the allocator that way, you're wrong in a dangerous way in a lot of the things that use the allocator model.
That's totally fair. Yes.
Yeah, if you assuming you didn't want to be parameterized on the allocator, I don't think there's anything implicit in that parameterization that obligates you to use the allocator instead of small buffer optimization. You could just pick to use the allocator.
That's another thing. It's a type erasing mechanism, so you have no idea if the thing you're type erasing even has an allocator. That would be very difficult to facilitate that implementation.
But since you're the one adding allocation, then having a way to parameterize that allocation is important for certain cases.
Well, not only do you have to parameterize the allocation, you have to parameterize whether you're even using allocation.
Well, you're already doing that. It's just what allocator do you use when you're using allocation.
Yeah. On the other hand, that's also an extra template parameter that is potentially unused, and that's not a very clean design in my mind, but.
Yeah, we didn't get to choose, and now it's done.
Yeah.
I can just tell you, you'll get NB comments and Bloomberg allocators. I would not be unhappy because if allocators vanished from the standard library, halfway is worse than anything.
Understood. Yeah. I guess one thing that could be encouraged is for any given implementation to provide an implementation specific, maybe like base class.
It's and the full allocator model is unnecessarily complicated. There are combinations of the features that no one has any actual use cases for and probably don't make sense. But yeah.
Right. I feel like I want to say something on that, but I don't really have much comment. All right. Oh, yes.
Has this been standardized yet? Or?
No. I think it's on target for C++ 29, but it's still in very early stages, so I would not make a bet on that.
Yeah, right now, on target for 29 is easy. we're not even opening the draft yet.
Right. Right. So, but there's many things that could go wrong in the process, and I certainly cannot predict them all because I don't have a lot of experience with that.
Yeah, they could push back for not having an allocator option.
Right. All right. Is that everything? Cool. All right. Thank you.